Good afternoon. Welcome to today's SCA webinar with Dr. Robello Samuel on how does well design, engineering, and real-time operation impact performance, efficiency, and optimization. Before I introduce Dr. Samuel, I'd like to remind the audience that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature. We will cover the Q&A at the end of the presentation, and you will be anonymous. Before we start today's webinar, we would like to ask a few questions about the audience. So I will be launching a poll. Okay, the first question is, what's your primary discipline?
I don't know if your screen is being shown.
Okay.
I don't see your screen.
Thank you.
There we go.
So the poll should be open. And what's your primary discipline? Let's start that again. Launching the poll. So I'm getting responses. We're seeing that 71% of our audience is petroleum engineering, 29% other. And looks like we've got most of the audience has voted. So I will close that and move to another polling question. And the next question is, how many years of full-time experience do you have in the oil and gas industry? So we're starting to get some responses now. And it looks like we have a good variety of different levels of experience. Most of you have voted, so I'll go ahead and close and share the responses. It looks like we had 11% with less than 1 year, 22% 1 to 3 years, 44% 11 to 20 years, and 22% have over 30 years. So thanks for joining us today. Let me make sure I'm still sharing. Today's presentation is how does well-design engineering and real-time operation impact the performance, efficiency, and optimization? Our speaker today is Dr. Robello Samuel. Dr. Samuel has been a chief technical advisor and senior fellow working with Halliburton for many years. He has experience in different drilling applications around the world. He's received a number of awards from SPE, including most recently the SPE AIME Honorary Membership Award. Dr. Samuel is an adjunct professor at several universities and has served in that capacity for several years. Sorry, I'm going back to my slides. And he has written a number of books, 13 books in drilling, and has 72 patents, 95 worldwide patents, and over 200 technical papers. So Dr. Samuel teaches several courses for SCA, including the one that he will be focusing on today. We'll provide you more information about when these courses are offered. The Applied Drilling Optimization course is going to be offered in a virtual format, live online, during the first week of May, and in an in-person format in Midland, Texas in late August. The Principles and Practices of Mud Motor will be offered live online, virtually, during early June, and in person in Midland in August. And Applied Drill String Mechanics will be offered in September in Midland. So SCA offers a variety of live online classes virtually. Several that are coming up in the near future include carbon capture and storage, an engineering perspective with Christine Illig-Economides and Dimitris Azignatou. That's the first week of May in a virtual format. It's offered in person in June in Houston. Lee Richards is speaking on drilling fluids in a live online format for 2 weeks during May. And Bob Barbet will be doing a virtual class on refrac candidate selection in early June. Dr. Richards has an upcoming webinar in May on understanding well control fundamentals, making well control simple and understandable. And of course, look to SCA for all of your training that can be offered in-house, as well as our public courses that are offered both in person and virtually. And SCA, in addition to training, offers consulting, direct hire support, and projects and studies. And so, Robello, I'm going to give you the presentation rights and let you start your presentation.
Hope you can see my screen.
Yes.
Okay, thank you, Susan, for your kind introduction. And I would like to take you through some of the condensed version of the 3 courses that I teach. It spans more than 72 hours, but I will take it on a high level in the next 30 minutes or so. To give a background, just you can go through these infographics. It is for a particular shale field, Eagle Ford. It has almost produced 1 billion barrels. It's now more than that. It has a lot of information, but I would like to concentrate very specific to the well design, the tubulars, all the things that are related. You can see it very well compares to the well-known oil fields in the world. You can see very close to the Gawar field in Saudi. And also you can see how much time it took for the US Gulf of Mexico to reach 1 billion barrels. So these are all the things that are comparing how much time it took at different time scales. But the important thing is we have drilled for a particular shale field 150 million feet of well path. Now think of that. If we could approximate 1%, if we have an optimized system, if we could save, that will result almost 2 million feet of well path. Not only that, you can see another important point that this particular shale play has taken is they have used a drilling pipe that can wrap around the world 1.25 times. In other words, that much amount approximately we have put the casings down hole. That is almost 165 million feet of pipes that have been gone forever inside there. If you think if we could save 1%, or if 1% is optimized, we could save 2 million feet of casing pipe. That is on the tubular side. So now, with this panoramic backdrop of drilling this extended length of a particular shale play, probably you can relate to some of this. At some point, you might have seen broken pipe, sheared pipe, twist off, broken threads, all these collapsed pipe, burst pipes, more related to the tubulars. As we deal with it, it's a complex system. Now, with this panoramic backdrop of the tubulars, if we go to the bottom, you can relate to some of the things. You can see I have taken pictures from different sources that we will see. So we have a system that is very complex. Now, how do it is easy to say 150 million feet of pipe used, and saving 1% is going to save 2 million feet. But what are the complexities that we need to we have to consider with, and what are the things that we can see when we model this? So, as Susan mentioned, I teach 72 hours of drill string mechanics, optimization, mud motor operation for a particular one. I just condensed it, few high level topics that you can see, and rest of the things it will be taught in the class. Well designed, drill string mechanics, drilling optimization, and how do we calibrate? We have a complex optimization techniques, all these things. How do we calibrate and realize the importance in the value chain in the real time? So some needs to be calibrated, some models have to be calibrated as we get more and more real-time data. And a lot of downhole tools we use. One special tool that we want to go through is the mud motor. We have a comprehensive mud motor operational class that spans for 2 days to 3 days. We will have the hands-on experience, hands-on practice of using and calculating different solutions. With it, I will take you through few high-level basics and understanding how they are interrelated. All the classes will cover the basics. Start with the fundamentals, because we need to have the basic knowledge. It is not that we need to develop equations, derive equations, but we need to have some basic principles on which these models are built over. So we have a comprehensive understanding of tackling any problems beyond the classroom teaching or education. So I'll go through a basic, simple example of mechanics. It's a thin and thick wall cylinders. That is well studied in the mechanical industry, in the chemical industry, as we handle all these things. But we deal with a different system. But we have to follow that slenderness ratio. So we have an inside diameter, outside diameter, length, obviously thickness of the pipe. So based on that, it is well defined D over T, or the slenderness ratio. If it is greater than 20, it is called the thin cylinder. If it is less than 20, it is the thick cylinder. Why it is important? Because that dictates how the stresses are going to act. So now, how does it relate to our system? So now I have given few examples. Most casings used in the oil field has a D over T between 10 and 35. It's a wide range, right? But if you nail it down to a particular pipe, say 5-inch drill pipe, using a 4.276 ID, you can see the slenderness ratio D over T is 11.78, which falls under the thick cylinder. So now most drill collars vary between 0.3 to 2.5. Most of the tubings between 5 and 16. So these are important as we develop the models. Now another point is, this is the cross-sectional dimension that we have gone. Now what about the lengthwise system, which we call the aspect ratio, length over diameter. The length of the pipe over diameter of the pipe. Think of a 40,000 feet we drill. It has an aspect ratio of 100,000. Very high aspect ratio that we deal with. We deal with a complex system. Now, the closest you will see is the high wind turbine towers or the nanotubes. And I will give you an example. If you take a human hair, I want to match with this, and you want to visualize it, it should have a 60 feet human hair that will have a 100,000 aspect ratio. That is the complexity that we'll deal with. One is the thin and thick cylinder. The other one is the aspect ratio. Now we have to model it, and we have to design the well that can handle these tubulars. Ultimately, we have to construct the well and also calibrate the models in real time. So the practical calculations are, we need to have the hook load, then the forces, stresses, and we have to limit all these calculations in order to find the failures, whether we are in the failure envelope. We don't want to exceed with a high aspect ratio system. And also it is not just a tubular. We have a lot of tools that we are putting downhole, expensive tools. So forces, we need to calculate the forces. It is easy to calculate the forces outside in a mechanical structure or anything, but when it comes to the downhole where it is immersed in the fluid, it becomes more complex. So we use two forces on that. One is called the true force or the effective force. It is a very confused calculation people think of, right? So I'll deal with this on a high level, but in the class I will give you more examples and go through the differentiation, why these are the two forces in play. So always we have depth and the tension, positive, compression, negative, and we map. So we immerse the pipe, say simple tubular all the way to pipe. Now it has a compressive force because of the buoyancy. So it is at the bottom, it is in a compression zone. At the top, you have a tension. Now at the top, we have the tension, or we eventually calculate the hook load. Now, is it the fluid force is going to cause the buckling? Is it going to fail the pipe on its own? We have found and also theoretically proved it is not, because the fluid forces alone won't buckle the pipe. You need to have the mechanical loading at the pipe. Now, if you apply weight on bit, it will move to the left. So we take the fluid forces or the hydrostatic force out of the true forces, then we plot it and we call the effective force. That is, the effective force at the bottom is now in the neutral point. At the surface, whether it is true force or effective force, you need to have only one single force. You cannot have two forces. Now, we take all the way from the bottom to the depth, which we call the stability force, fluid stability force. That makes the system stable when we have the hydrostatic force. When we start applying the mechanical loading in form of weight on bit, both the lines, the true force and the effective force, equally move to the amount of weight on bit you apply at the bottom. So now we have a limit on the right side, which we calculate based on the yield strength of the pipe. On the left side, we make it as a buckling limit. It is not a failure limit. We calculate the sinusoidal buckling and helical buckling based on analytical methods, and we plot that, and we want to stay away, if we want to stay away from helical region or sinusoidal region. So these are the limits that we take into consideration. One is the limit of failure, the other one is the limit of buckling. As long as the forces are within these conditions, we attend to okay, and also we calculate how much is the overpull between the top at the surface and the limit forces. Now we have to take this into a higher level. The force we calculate. From that, we calculate at each point the side forces, the bottom forces, the top forces, and we start integrating all the way to the surface. Now this has to be done for all the operations. We have to have the drag calculation, torque calculation for tripping in, tripping out, rotating on bottom, rotating off bottom, sliding, back reaming, and the other related operations. So this forms the basis for all the force calculations. So when you take the torque and drag, it not only calculates the forces, but also includes for all boundary conditions that are related to different operations. Based on that, we can calculate other things like rocking and what are the effects of the friction, and the more into the friction calibration, friction calculations, drag forces, side forces, that will be covered more on the torque and drag class. Then we have to take into effect of the butt properties, weight on bit, surface pressure. You may circulate and apply surface pressure. These are all the parameters that the parameters have to be included in all the calculations. So it becomes a comprehensive calculation. Start with a simple friction basics, then develop the friction force or the drag force. From there, you solve the equilibrium equation. Then you start to calculating the forces at each component. Then you move all the way to the top. And the boundary conditions for tripping in, tripping out, rotating on bottom or off bottom, sliding, back creaming, all these things take into consideration when you start calculating the drag forces and the torque estimates. Now, when it comes to the torque and drag model, there are different models available. One is the soft string model. The soft string model is the well-known model that is used in the industry for a long time. Some basics, no bending stiffness considered. String is assumed to be a cable. If I have a 40,000 with an aspect ratio of 100,000, if I hold it, if I have the ability to hold it, it will be like a cable. So the assumption is valid for a long string or a long aspect ratio string where the bending stiffness becomes less important. So you have this calculation, then it assumes whatever dog leg it assumes it is going to follow. So now the contrary is it true? Now if I have a high dog leg, the pipe, if I take 30 feet pipe, it may not go or 90 feet to stand. So we need to consider whether the forces calculated and thereby the stresses, are they correct when we use the soft string model. For the hook load calculation, it may be okay, but we need to estimate the accurate stresses when it considers the right side limit of yield. So slipstring model was introduced, and it's also a long time back. This is introduced, and it is still there. As far as I know, we have introduced almost 30 years back. So it includes the tubular stiffness by its nature. It is a stiff string model. It increases. It does not assume the string is in constant contact. As you can see in the wellbore, it can touch at the different places. So the contact points are different as compared to the soft string model where it is continuous. Here it is different places. So the contact forces or the side forces estimated are not the same as in the soft string model. And thereby the forces may be different at the different places. So it determines the exact position of the string in the wellbore. So on a 3D space where you can see it can move up and down or high side, low side. The problem with the stiff string model is it by its nature, it has a time penalty, the computational penalty. It takes a lot of time to calculate. So for fast calculations, it may not be suitable. So the problem is for easy, quick and dirty, or the quick and easy solution, the soft string is very fast. For real time, if you want, okay, I need 1 second result, soft string is, it runs in microseconds, milliseconds. So soft string takes time. So people shied away in using it. But when it comes to a high dog leg, stress is of concern, then it is easy to use it. And now most of the software, including the WellPlan, provides a free option. You can just select both the models and compare it with. So later on, the problem is shifting is taking more time. So the question is, do we need the shifting model all the way in the wellbore? Can I bypass a shifting model? Do I need to use soft string all the way? Is it conservative? In some places, it may not. So I introduced a hybrid alternating model where automatically, if it is needed, stiff string will be run, then it will switch to soft string when the results are very close enough. At the same time, the displacement and the forces are not compromised and it is continuous. So that is the third method. So that will reduce the time which the stiff string model is about. Then these are all static models. If it is a tripping in, what we do is you just keep the string at one depth, analyze it, and move the string to another depth and analyze it, and start showing the results in a cumulative manner. Is there a way that we need to do real-time transient model when we start comparing the real-time analysis? For that, we need a transient model. The hook load at a particular depth may not be exactly the same when you are pulling up, slacking off, or removing from the slip, all these things. So we need to capture the transient nature of the hook load when we start calibrating and going for micro-invasive analysis of slack off and pick up drag. For that, I implemented a transient dynamic model, which gave a lot of interest in the results, which matched very well with the real-time data with a high-frequency data streams. So these are the models which will be explained more in detail in the class. So next one is the tubular failures. We have calculated all these things. We have a good prediction. Now, what are the limits that I have shown? Failure, that is the important one that we see, and we use the traditional mechanical failure approach, material failure, structural failure, go through the static failure analysis, whether it is brittle or ductile, where the stress strain curve is different, what you can see. And if it is fatigue, a lot of companies do more time-based fatigue analysis. On a static torque and drag, you can see a simple comparison of quantifying the magnitude you are going to fail if you are not taking proper precautions. I'm not going to cover on the buckling. Buckling is a difficult left side failure. I'll cover more in the class. So continuously on both the sides, limit curves, there are four forces, right? Internal pressure, external pressure, real force, effective force, then the torque. The combination is important. So we use the von Mises failure criteria to compare the limits. So as long as it is within the von Mises limit, we are good. So it gives a failure limit of von Mises. So we have all these forces taken into consideration. And also you have to see, we have to find the pressure difference. Pi, P0, the burst, the collapse have to be considered with. Probably on the drilling side, we may not encounter this, but when we float the casing, when we run the casing, these are all important. So the coupled variables with axial loading is important. And it has been well studied and well documented. We'll go more in detail as we study through this class. Other topics of interest in the design of the tubular design is pipe stiffness. As we have seen, pipe stiffness, how do we transition between the pipes, drill collars, heavy weight, all these things, bending stress ratios. then the important one is the friction. That is the starting point of all the torque and drag calculation. Now, static friction, do we consider kinetic friction? With the static models, always use one friction factor or the friction. We don't use the Coulomb friction. We call the friction factor to wrap all the uncertainties into this one calibration factor. Now, neutral point. We have true forces and true forces and effective forces. You saw the neutral point differing. Which one do we use it? When we do the soft string model, how do we magnify the stress? I don't want to use the stiff string model. You're saying the stresses are not properly calculated. It may be underestimating it. Okay, can I magnify it still using the soft string model? Bending stress magnification factors are introduced, so that will magnify to a certain level so that it matches with a stiff string model. Ultimately, it may negate the positive side of the stiff string model if it is properly applied. Then buckling limit factors. I have not covered the buckling in this session, but you will see a lot of buckling models, 7, 8 buckling models with different coefficients. Which one to do it? They are analytical models done in a lab, verified in a lab of 50 feet pipe, 8-inch pipe with a aluminum pipe. Does it work downhole? We have seen differently in a test well of 2000 feet. The traditional way is sinusoidal buckling, helical buckling, and lockup. We have seen sinusoidal buckling and straight away going into lockup without passing through the helical mode. So these are the things, how do we calibrate? So buckling limit factor is the one that will help you to calibrate the buckling models. Then bending stress strength, which I have covered earlier. Then overpull calculations. Overpull calculation, how much margin is needed if in case the string is stuck? What are the effects of the pipe in the hole? What are the pipe strengths? Do we know the pipe class? What about the effect of the temperature duration? So these are all the calculations that we need to take into consideration. Then it is overpull. Then comes the slip crushing. When you're pulling, now you're releasing the load on the slip, whether it can handle. It can hold. Most importantly, when we have a very deep wells in offshore, that it is important. That the torque and drag models can help in estimating it. Finally, casing wear. The pipe that is being worn out, how much it is getting degraded. We don't consider a lot. All these Eagle Ford wells, I was planning to estimate how much casing has been worn out approximately. So the casing wear is an important one on the well integrity value chain. But it hinges on the torque and drag calculations, which I will show in a later slide. So casing wear, it is a puzzle. Contact force, wear factors, groove positions, wear logs, wellbore. Now contact force, where we have a friction factor. Now we have a casing wear, that has another wear factor, which was done 30 years back. Now I have initiated a JAP, and with new materials, the technology has changed. It's no more a black box. So more details are emerging from the new wear factors that will be integrated into this calculation. And we can calibrate also later using the wear logs and other surveys. Now the question is, we have two models, soft string, stiff string. Contact forces are not same as soft string, where stiff string has a well-defined contact point based on the model as well as on the wellbore. Now, if the contact points are not properly estimated, then your wear factor, wear estimation, casing wear, volume wear is going to be wrong. In the soft string, it is going to assume it is going to touch all the way, whereas the stiff string model will take into consideration where the contact points are, and that also on 360 degree. where you can see the groove overlapping depending on the operation. You may have a different contact point when you're tripping in, and when you're pulling out, it may be a different contact point. So where grooves may not overlap. So sometimes we may overestimate. Soft string may give a conservative estimate, is not true all the time. You can see, as I said, it can touch at different points in the same well, and it may be different for the same depth for different operations. So this, I tie it with all these things to the well design. Eventually, it all depends on the contact between the well bore and the string. I started with string. Now we have to go with the well design. I'm not going to cover different types of well designs and everything, but in the classes, you will see how they are related and how you can quantify it and estimate it in a coupled manner of well design and well path and the string design. So it gives quality of the well bore. Lead side forces are important, which you can see running of the logging tools. Well bore stability, the direction that you need to go. Less side forces, less tortuous, and less impact on the tools that we use. And if the string is vibrating, I have not touched upon the drill string mechanics, vibrations, and drill ahead. That is another topic that we need to deal with. So what happens when we start, when the string starts vibrating? The impact forces are important. How much is the magnified contact force? How much it is going to affect the casing wear? So we have to reduce the side forces. The well path can be tweaked in such a way that these forces can be reduced. Thereby, you have less torque, less drag, and also artificially induced well bore destabilization and higher increased well bore sizes. So well path optimization is important. When you look at it, optimized well planning methods, there are different methods available. Now, one click, you can get a different optimized well path. Not only one path, you can also in a pad or multiple pads or multiple wells. Optimized tortuosity method, dogleg severity, or you can compare the absolute and relative tortuosity. And there is another one, well bore torsion. That is important. Torsion is different from tortuosity. Torsion defines how the well bore is twisting with reference to the plane of space. So that can tell how the well bore is spiraling, whether it is a right-hand spiral or a left-hand spiral. Always we talk about right-hand walk and left-hand walk of the bit, but how the well bore is spiraling is important. At some point, it can flip based on some of the survey analysis. Another one is the well profile energy. Based on this coupled well path with the drill string mechanics, you're connecting through the energy or the strain energy or the bending energy or the twist energy so that you can minimize not only the well path but also the energy on the string. Then drag force minimization. Another one is considering the productivity of increasing the lateral length. We cannot increase the lateral length as we want. Not only on the mechanical limitation, but also the hydraulics limitation, production limitation that we need to take into consideration. So these are all the important things that we need to do it. And it ties back to the infographics I said. Each and every incremental change, that will result to more than 2% that we want to do it. Reservoir exposure, which I have touched upon, well, both trajectory complexity, incident angle, different catenary design for extended reach, torque and drag, all these things. Now we can drill a long lateral length, but the question is whether we can run the casing to the bottom is important. That is the runnability of the casing. If we cannot run a casing or a completion string, then it is of no use just extending the lateral length. So these all have to be tied with that, which will be covered in the length optimization. Speaking of optimization, it's a 3 days class which I cover extensively, optimization and real-time optimization, but I will go through quickly a difference. And still the industry is confused between the performance, efficiency, and optimization. I will give more examples in the class, but I will just go through, skim and hop through some high-level slides. What is performance? It is measurable, dependent on achievable, relevant, and based on time. We have a KPI, then you fix a performance and performance criteria. If it is achieved, now everybody is achieving. Next year you move the scale, then you compare it. Efficiency, we clearly know, right? Input and output. It is the ratio of output that we are getting to the input that it is into the system. Similar to mechanical specific energy, where you are putting energy into the system, how much you are getting. Operation dependent upon output, and efficiency that we can calculate, and it takes it involves the risk as we move closer to achieving higher efficiency. Now, optimization is a mathematical technique or a heuristic method that you find out the maxima or minima. That is the objective function, that what you want to achieve, subjected to some constraints. People, process, technology, you have different constraints. Now, weight on bit is a constraint, flow rate may be a constraint, pressure losses may be a constraint, and what do you want to achieve? Whether you want to maximize ROP or you want to minimize energy, all these things, that needs to be taken into account. So a lot of topics by nature on its own right, you can do optimization, just well path optimization or wellbore optimization or flat time reduction. But you can also do a system approach of a comprehensive optimization. Then it becomes a very complex conditions with multiple variables. But all I want to see is a simple 2D chart or a 3D chart, weight on bit and RPM. What is my torsional instability? Where is my lateral instability? What is my maximum weight on bit that you can apply? I can apply without failing. What are the ROP? As the bit wire couples, how does it go down? Degrades. Hull cleaning, maximum RPM in case of mud motor. What is the stall RPM? All these things. MSC, hydromechanical specific energy. I can narrow down based on this constraint what is my stable optimized region. I can consider this as the opto-satisfied condition where I'm okay with this. All these conditions are not going to happen, and still I have a complex system. So I may not be able to exactly narrow down this space. So I have an uncertainty or probabilistic estimate over this so that I have a probabilistic optimization model. Now, hydraulics optimization, the traditional HSI and impact flow which are used, but I will show some of the pitfalls if you are using mud motor. It is completely different because it is an energy converting machine that we are putting inside. That needs to take into consideration. Dynamic optimization, as we move on to the real time, I think there is a typo. It's a real time physics and the data driven model that takes into consideration of both the microservices in real time and come up with an overlaid uncertainty model. This is a three-way coupling. Usually people talk about data driven. You give me data, I can use some glorified regressional model and fit it and predict it. It's not. It doesn't know the physics. It doesn't know the domain. Physics, it knows the fundamental physics, but we built all these things based on assumptions. So the both will handhold in such a way that maybe 70% physics and 30% data, or 30% physics, 70% data, so that they adjust the model in such a way that you have a better prediction. And still we deal with a high aspect ratio system. Lot of uncertainties. We don't have a lot of sensors. So we have the probabilistic estimation. If your input are stochastic in nature, output is going to be in stochastic in nature. So this gives a three-way coupling that we need to use it. That is much better than the hybrid model. Now people have introduced a hybrid model few years, maybe 10 years back. Now this is a three-way coupling that will have a better prediction as compared to the pure physics or pure data. I will touch upon only one component, mud motor. Mud motor has a long history, impulse turbo drill, single stage. Then we started using percussion hammers in '84. Then came the PDM and the positive displacement motor. Now we call generically as the mud motor. Electrode drill motor, G introduced, then retested. It didn't get into the traditional daily use, miscellaneous downhole motor. But I will concentrate in the class on the mud motor. What are the intricacies? Very simple machine that could not be silenced in time. It was once the workhorse of the industry. Now it has become a racehorse. So that is the one, why it is positive displacement, why motor, what are the different configurations, what is the optimum selection that we can use, different types of configurations and lobes and even wall, how we can use under different scenarios. What are the failures or the losses, even though they are very good. Now it can drill vertical, build and lateral, but still it has limitations that we need to do it. And what happens when we put it in a motor configuration? Always use the 3-point configuration, but what are the fallacies? What are the failures? What are the pitfalls of using this model? And how you position the Benson along with the mud motor that will be covered. Then mud motor operational roadmaps will be comprehensively covered in this class, which covers the power section detail, different designs, operational envelope, performance curves. What are the effects of using the traditional surface measured performance curves to calibrate the downhole performance of the motor? What are the effects of pipe rotation? That is, when the mud motor is in the rotary mode, what are the limitations that we need to do? Sometimes it will go into the pumping mode rather than a motor option. Pipe rocking and motor operation, MSC, how the traditional MSC equations are valid. There are a lot of wrong equations given in the industry, but we have to consider that also. Dynamics of the mud motor, what happens when you have a mud motor in the system? It is an inherent source of vibration because it rotates eccentrically. So how do we take into consideration when the mud motors are used? How the prediction of vibration frequency from the software are reliable when a mud motor is there. So I'll cover that also in the class repair and maintenance, of course, the final one. For all the classes I teach, you will get a free book, either Applied Drilling Engineering Optimization, I think 400 pages, 5 unsolved problems of calculations, and you can see the problem and the answers, solutions. Then mud motor, there are 2 books. One is the mud motor, basic design, 400 pages, and mud motor and well engineering, another 400 pages. So you get one book along with the class. With that, thank you for listening and happy to answer any question, and I will give it back to Susan.
Great, thank you, Robello. I want to remind our listeners today that you can use the GoToWebinar question feature to pose your questions because you are muted and you will be anonymous. And I'd like to thank you for attending today's webinar. Later today, you'll receive a link to the recording of the webinar, an evaluation form, and a link to register for Dr. Samuel's class, Applied Drilling Engineering Optimization for Drilling Engineers. It's scheduled for May 2nd through 5th in live online formats. That's 8 to noon Central Time, and August 29th through 30th in Midland, Texas in person. Dr. Samuels also teaches applied drill string mechanics for drilling engineers and the principles and practices of mud mortar for SCA. So be sure and put your questions in the chat. Dr. Samuel, you talked a little bit about how the mud motor has gone from being a workhorse to a racehorse. Could you expand upon that comment a little bit, please?
Yeah, earlier, that's a good question. Workhorse, it was used to just for site tracking and other things, right? So very specific purpose, whether it is a mud motor coring or site tracking or deviating the well. When it is needed, they go for mud motor. Now the shale play has completely changed the landscape. Now they say, okay, rotary steerable came. Now that's the end of mud motor. That is the final nail on the coffin of mud motor. What happened? We use mud motor behind rotary steerable. We need power to rotary steerable. It's called the motor assist rotary steerable. Agitators use power section of mud motor. Now with the race horses, okay, I need to have the mud motor that can drill my vertical, the build and lateral in 6 days. Can you give a mud motor? We are reaching the point that you don't need any other tool. That is the fastest tool that it can rely upon that goes in one run, right? That's where now earlier, okay, lateral section we'll use mud motor. Then it became, okay, can we use it in, no, it was in the curve section. Then, okay, can we use it for the rest of the well? Then can we use it to the vertical? We are talking about in hours, right? We don't talk about vertical, curve, and lateral in days. So that is, it may not be the racehorse for the world, but it is definitely the racehorse for the shale plays. But eventually it will, yeah.
So you focused on the Eagleford play in part of your presentation. Could you talk about the challenges that we might encounter with H2S in the Eagleford and some of the drilling techniques you've been discussing?
Yeah, H2S is completely, when it comes to toxic gases, I think it is completely different because the corrosion handling of the tubulars are important. I don't cover much on the class, but I'll try to cover the deration or how to derate the pipes based on the strength and what are the special pipes that we need to take into casing designs and other things so that we have a long-term sustainable production. We have to consider two things. One is the drilling through H2S, and in some places it may not have, and after a long time, due to injection of water, brine, then it becomes a H2S producing well. Then we have to take care of the pipes too. So these are two things specifically on the casing side. I don't cover more on the casing design per se. To your question, H2S is, I think, not covered on the classes.
Okay. You spoke about the sinusoidal buckling method as being the traditional method. Could you give us some more information comparing that with the helical buckling method?
Yeah, it's the traditional lab tests have revealed, and also the industry standard is as you apply load to the string or compressive load at the bottom, the string goes into bending. Then it's sinusoidally buckle when the buckling limit of the pass lay force is exceeded, and it moves to the sinusoidal buckling, or it is called the lateral buckling or a snaking buckling. Now, if you start applying more and more, it goes into a 3D mode of helical buckling with a certain pitch and amplitude, which is constrained by the well bore. Then you start applying more and more. Now if the friction is along the string, along the wellbore and the helical pipe, now you apply more and more, then it will go into lockup, where the transmission of surface weight to the bottom weight on bit is 0 or 2% something, right? Whatever limit you can put. Then you go on apply, it may go into permanent deformation, then you cannot go back into the elastic region. So that now people have, researchers have developed at what force it is going into sinusoidal buckling. Then what force it is going to go into helical buckling. So it is 2.14, all this, some coefficients, the researchers have come up with different coefficients compared to the, so you just multiply by the coefficient of the sinusoidal buckling force, that will be the helical buckling force. Now, which number is correct? 2.4 or 2.45 or 4.1 something? So it doesn't translate the downhole. That's why there are calibration methods. We can do a simple test of, or if you have downhole weight on bit sub, it is easy to do it. So that we can go through that more in detail on the class, unless we put some numbers and show, right?
Very good. And could you compare and contrast the with the torque and drag, the hybrid alternating model with the dynamic model? I think you said it helps to capture the transient nature of the hook load. Could you tell us more about that?
Yeah, the hybrid model is now I will quickly explain. Now you're in a tangent section, pure tangent section, no undulation. Now you put a pipe, it will be always on the low side. Right? Now I do the calculation using soft string and stiff string. It will be very close. So it may not have any effect of running, say, 10,000 feet of tangent section in stiff string, getting almost same result. So obviously, even the displacement also along the wellbore may not be different, leaving aside the end side. So for that, I don't need, I can switch to soft string, then automatically at certain point, it will switch to the stiff string, where the stiffness have to be considered. So there is a method that already I published it. And also soft string in a place where we may consider soft, it may not be, right? Now, based on the stiffness calculation, we know at what point we need to go switch into soft string or stiff string. And also, we don't want to do it every feet. Okay, soft string 1 feet and another 1 feet stiff string. So it is the length that automatically it will find out, then it will go into the next sweep. The transient model is dynamic. The friction is not in one direction. As the pipe is moving, pipe can move up and down, the friction direction changes. Whereas in the traditional static model, the direction is only one direction, right? If you are tripping in, the friction force acts in the other direction. But when you have the inertia force, that when you are tripping in, the pipe can move up and down also. So the friction can reverse, which will be taken into account in the transient torque and drag model, which you can also read it in the SP papers, but I will cover more on the details of the model where all these three models will fail. The transient model will give more predictive results at what from 0 to say time 1, then time t1 to time 2, probably it may be matching with all the static models, then time t2 to time 3, it may be oscillating. It will be more of use in the real-time calibration to find out more slack off and pick up drag, and also when we move into the automation mode.
The next question, why would you recommend an RSS over a mud motor for a deviated well with an inclination angle of 36 degrees?
What RSS?
This is
Yeah.
what they wrote, RSS.
When do we use RSS?
Yes.
Yeah, but in this class, I don't cover RSS. I think it's mainly on the mud motor side, targeting the shale plays, and RSS also used, but it's not a issue to include. When do we use it? And because not all the shale plays use mud motor, right? So
Right.
it's a combination. Wherever it is needed, it is needed, and it also there are models that when we use RSS, when we use mud motor based on the cost, and ultimately how do you optimize it based on the lateral length. That's why I always call the motor as a racehorse that can match with the rotary steerable.
Very good. We've reached the end of our hour today, so thanks for attending today's webinar. Later today, you'll receive a link to the recording of the webinar with an evaluation form and a link to register for Dr. Samuel's class on applied drilling engineering optimization for drilling engineers, scheduled for May 2nd through 5th, 2022, live online to noon Central Time, and August 29th through 30th, 2022 in Midland, Texas, in person. Dr. Samuels also teaches applied drill string mechanics for drilling engineers and principles and practices of mud motor for SCA. Thanks for attending. Goodbye.